I'm Peter, and I co-founded Auxorio. We're working with ZK audits with my partner Lev Menshikov. He's also today will help you guys to build the secure ZK circuits. If you would like to participate, there is a great sponsors like Scroll and Polygon and Aztec. All of them are working on ZK, and this is where you field, and so many typical mistakes people always repeating with their code. We are here to help you to understand how we can mitigate these things and what is the what the basic things and how we can protect your code from attacks. So we will start, we will introduce you like 7 most common things, like basic attack vectors and how to protect them, and also bring you some real world examples of the errors and attacks that was happened in ZK field. Okay, I would like to start, and I think I will give a talk to Lev. We will start from our first, most basic thing, most like basic attack that you can see that every beginners happens, because ZK circuits, they are very different from original, like from Solidity or other things.
The first type of vulnerability is under constrained and non-deterministic circuits. We have merged them into one type just because those two types and non-deterministic circuits in vast majority of cases is simply under constrained circuits that additionally involve the break of determinism principle. So we have decided to merge them. So I just cannot operate. Oh yeah, I can move it. So to understand that vulnerability, well, first of all, let's define what are constraints in ZK circuits. Circuits are generally just a bunch of mathematical checks that are packed into mathematical equations that are stored in a one CS file. So, and if prover passes all of them, for programming just means that he knows the secret witness, and then he can produce a correct, a valid proof for that witness. If there are not enough constraints, it just means that there are multiple ways to generate proof. It means that we can produce several nullifiers, and then the logic and the actions of our prover, of our malicious prover, will be unaccepted to us, and it means that just our circuit is vulnerable. So, and also we have to possess that if our circuit is under constraint, it just means that we cannot provide our users with the guarantee that our proof is legitimate and our soundness principle is broken. Let's move deeper. To understand that, let's see the following code example. As you see, it's just the template that takes 3 signals. The first 2 are just factor inputs, factor 1 and factor 2. And our program just checks that the product of those 2 signals is equal to our public signal val. And guys, this question is to you. How do you think? How many problems here? And you have the ability to watch it by yourself and write it into the chat while I'm going to explain that. So there are 3 core problems here. First is that our template doesn't check that the factors are not equal to 1. The second problem is that it doesn't check that the value of multipliers is positive. And the third one is that the product of factors is less than the order of the finite field, which is the typical example of wraparound effect. So we will talk about that in the near future. So you can, yeah, you can see it here. So if our field order is 100 and our val is 10, we can just, if we are malicious proof, we can just provide 10 and 11. We will get 110, which is more than the field order, and then we will have the ability to create a malicious proof that will be valid. Um, and also we have some part of the example of under constraint circuit. So if our public parameter p is 9, so there are four cases in which we can create a valid proof. So -3, 3, 1, and -1. All those inputs will be correct for our under constraint circuit, but of course, determinism says that we can create only one valid proof for one secret witness. So our proven system just have some bugs, as you see. Yeah, we have already watched this. The second one is arithmetic overflows and underflows. It's quite basic. So it's just about when incompatible inputs are used together, and we will see that. First of all, we have to possess that this vulnerability occurs due to the mathematics behind prime finite fields. As you may know, it is all about linear algebra and modular arithmetics. So, and to first of all, let's understand what are prime finite fields. It's just algebraic fields that allows us to perform addition and multiplication modulo p on the set of elements that are constrained by from 0 to p minus 1. So, and overflow occur when the result exceeds upper bound, and underflow performs when the result is outside of the lower bound. So the classic example of that vulnerability is semaphore double spending vulnerability, which was conducted by Roman Semyonov. Yeah, Peter.
And this is a real example of like our friend that found that there are so many libraries that work with zk are vulnerable for double spend. And that happens because in solidity you use field like in power of 256, and most of zk circuits work on the bn254. And when you just port numbers to the circuits, you just get classical overflow issue. And this bug affected by like more than 10 working projects at that time. So it happens in 2019. Yeah, and we want to describe this example very briefly. So how it works, pretty straightforward. You just get very big number and get overflow, and when you check the balance, you can easily find the two witnesses that will give you the correct example, so you can use it for double spend. um, so the next one um, is I don't think we will go into the deep details here. So I think we can skip like to the basic thing. You can check the Kobe fix it quite quickly in Ziki drops, and Circum was affected. Everything was fixed, and luckily nobody was affected by this issue. But this is classical overflow that really uh, principal things that you have to worry there. Okay, the next one is mismatching bit length. So also, like, you always work with a bit and bit masks in circuits, and it's very easy to just just found that you can skip some check inside, and if you will give signal with the more bits that is assumed to be calculated inside, that then you can get the mistake that give you wrong output. Maybe Lev, you can give some more examples here.
Yeah, on the slide you just can see the classic attack scenario when we have an input zero that has a length of 3 in binary, and 9 which is 4 bit length in binary. So and we have a mismatch here. So in the result of processing, we just can see that um, it, 1 is more than 9, which is of course is back. So that's the classic example of that attack. Yeah, and the mitigation strategy is just to use num2 bits included components. You just wrap them and constrain your inputs using that, and then you give those inputs into our less than vulnerable program, and all works fine because we then just ins- ensure that our input is less than the second input. So all works okay in that symbol.
The next one is not quite, uh, but it's not obvious one. It happens with unused public inputs. Uh, if you use signals and public signals that you will not use, it could be optimized by and the at the beginning it looks like it's not a problem, but for example, if you use and your proof should be unique, it can cause some wrong assumptions for, because malicious person can give you different kind of signals. For in this example, like signal 3 can be any kind of signal, and if he provide input 1 and input 2, which is correct, he can use any public input 3. For example, in semaphore, for example, the next slide is attack scenario. In semaphore, when you use zk for sending anonymous messages, malicious person can generate as many proofs as he want with different kind of messages.
Yeah, with the same basic inputs. So that's the problem. And the core mitigation strategy is just to use those variables in some logic, in some mock logic that are not in demand, but we declare our using variables, and the all is fine. Optimizer doesn't ignore that, so all works okay.
Mhm. Okay, we have the last 2 minutes, and let's go like very briefly. The frozen heart is a general um, name for a set of the errors that accompany the trail of bits. You can check the zk docs links, and there are so many problems happened with them. Um, for example, with the broken of soundness, and it's also related with trusted setup leak. Yeah, I think we will talk together, um, because of very common thing, and that happens in 2019 with zcash initial ceremony, because of incorrect operations with toxic waste and different kind of parameters there was interconnected with each other. So but it should be independent. But lately, the researchers from Zcash found that you can recover the toxic waste, and you can generate the proofs, and you can emit as much money as you want. Luckily, they fix it in next update, and nobody affected. Um, So we will skip the trusted setup mechanism. So because of lack of time, I
It's
will
quite
tell
basic
you about
code.
the
Yeah, we can just
yeah,
skip that.
and about but just check that you use standard libraries and use some basic things. Don't try to write your own cryptography. This is the most important thing. And the last one is just very minor thing. Looks like sometimes coders misplace constraints in variables. So sometimes you think that you put more constraints and check some variables, but actually you didn't it. You can find it in many circuits, these kind of problems, and it causes the potential malfunction of your programs. So here is example. The very basic example. You can check how it works. Lev, do you want to add something there? Or you...
No, it's quite basic, I guess. We can skip that.
Yeah, okay. So this is the end. It's time to hack. In conclusion, I just want to say like programming of zk snarks is not the typical programming. Check how finite primate field works. Check more how you have to build these constraints, because there are so many things that mm, works completely different in circuits rather than in normal Solidity programming on other languages. We will here to help you. We show you the 7 common bugs and pitfalls. Of course, there are much more, but this is the basic things, like same as in Solidity, like double spans. Everyone have to know about this. You have to know about these basic things, and we're here to help. If you want to build circuits, you feel free to contact us. Happy hacking, guys, and I hope you will be fine and safe. If you need any advice, feel free to ask me or my team, Axorua. We're very welcome to help with the consulting audits and just to help new hackers to dive into this field. Yeah, so feel free to check our blog. We have a lot of research papers there, and happy hacking. Thanks.